All right, section 7.3, the washer method. Excuse me. So let's go ahead and get started here. Our objective here is to apply the washer method to basic volume problems or solids of revolution type problems. Okay. So and we're going to talk about this in the warm-up problem as well. But previously in the disk method, we had situations where the area that we were rotating kind of was perfectly up against the axis of revolution. When we're using the washer method, we have a different situation. So we have a situation where the area is not up against the axis of revolution. So just to draw a very simple sketch of what I'm talking about, and just to focus on subregions, so I'll put in a little rectangle here. So in its simplest form, we have the rectangle, the representative rectangle, is being spun around an axis of revolution. And there's a gap, okay? So there's a gap that's created. And so in that gap, we have a small radius, an inside radius, little r, and then we have the outside radius, which we'll call big R, or capital R. All right? And so when that is spun around, what we end up with so we're going again around this axis. So what we end up with is, this is not going to be a wonderful drawing, but we end up with this washer looking thing. Oh, missed it on that one. Okay, so it's not a great washer, but you can kind of get the idea. Okay, it spins around, and it's like a disc before, but now there's a hole in it. Okay, so if we call the width of the washer, or the thickness of it, W, then our formula for the volume of this thing will be the outside. Well, there's a couple ways you can think of it. Usually students will start off going to the big cylinder minus the little cylinder. If you factor a pi out of that, remember pi r squared h is the volume of a cylinder. If you factor a pi out in front of that expression, then you arrive at this formula. In fact, you know what, I'll just show you. So pi r squared h of the big cylinder would be pi capital R squared times W. The height, again, we're calling W here, so pi r squared h becomes pi r squared W minus pi little r squared times W. When you factor out the pi, you get this. And we're going to factor out the W, but we're going to put it on the other side, and you'll see why in a second. So this will be capital R squared minus little r squared, and then we have a W here. Okay. Now the width or the thickness of that rectangle is going to become the dx, right? If we're going around a horizontal axis of revolution, then the thickness of that rectangle will be dx. The pi will stay out in front, and if we're going to take an infinite number of subregions, it's going to be from a to b, the integral from a to b, and then the radius is going to be defined by some function in terms of x squared minus some function, the inside radius, which is a function defined in terms of r squared. All of that will be integrated with respect to x. Okay, so there's your formula for washers when you're spinning around a horizontal axis. And that's what I was saying. Oh, so if you go around a vertical axis, all of it's the same, capital R, lowercase r, but everything is in terms of y, and you go from bottom to top. You go from C to D. All right, so I'm not going to write that all out because it's similar to the disk method, except that the formula changes. So, first example. Suppose we want to take and find the volume of the region bounded by y equals square root of x and y equals x squared, right? And we want to go around, revolve the x-axis. Okay. So let's sketch that out real quick. So square root of x does something like this. X squared does something like this. Okay, they meet here at 1, 1. Okay, and so if you imagine spinning this around the x-axis, if you put in and you draw in your representative rectangle here, when you put that in, you can see that it's not going to make discs. Each rectangle is going to make washers, and so you can kind of imagine what this is going to, what kind of a volume or solid this is going to make. It's going to be sort of goofy. Missed it a little bit, but let's see. So something like this. Here, you can go. Whatever, you get the idea. Okay, so you get sort of this goofy looking solid here. And to find the volume of that, what we're going to do is kind of fill in all the pieces from the formula, right? We need to know what the big radius is, we need to know what the small radius is, and then we need to subtract those in the context of the integral. So what we'll do is we'll look for the big radius first. So the outside radius is going to be defined by this top function, which is square root of x. So capital R of x is equal to root x. The inside radius, the smaller radius, little r, is going to be defined by this curve here, which is x squared. So little r of x is equal to x squared. We're shrinking the rectangles in the horizontal direction, so dx is our differential, and then we can set up the integral. So the integral will look like this. V equals pi times the integral from, let's see, so we're going to go from left to right, so from 0 to 1. Of the square root of x squared minus x squared squared, all of that with respect to x. All right, and so when we compute that, which we could do pretty easily by hand, I'm not going to though, you get 3 pi over 10 for the volume. Okay. So again, you know, I don't know if I said this the first day or in the first video or not, but I just find this concept is really interesting. This is not a, you know, this is not like a sphere or something simple, right? This is an odd solid, but we can find the volume of it exactly using calculus. Okay, let's do one more. This would be a good one for you to try and try on your own and see how it goes. So go ahead and pause right now, well, as soon as I get the problem written down here. So let's take the region y sine of x. Y equals cosine of x. That region, excuse me, from 0 to pi over 4. There's lots of regions bounded by those two things, those two curves. All right, and then, so we'll take that and revolve it around the x-axis, so around. So, okay, now would be a good time to pause and see how this problem goes. So I'm going to start off by sketching the area here. Okay, and so this is at pi over 4, comma sine pi over 4. Or cosine. They're the same. All right, and so then when you revolve this region, you get something kind of like a bowl, I think. Something like this. All right, and so again, we're going to use the washer method, so I will sketch in the representative rectangle here. And actually, you know, if you don't know what method to use, you can just start off by sketching in the rectangle. And you'll see that when you spin one rectangle, you're not going to get a disk, you're going to get a washer. And so you go for the outside radius, capital R, so R of x, capital R of x is equal to, let's see, that'd be this top function, which is cosine, so cosine of x. And then little r, which would be in here, so that'd be the inside radius, is going to be defined by this function here, which is sine of x. So little r of x is equal to sine of x. And then you can take and find the volume from that. So, and also you can see the thicknesses in terms of x here. So we'll take and find the volume, which is pi, integral 0 to pi over 4, and then it's going to be cosine squared x minus sine squared x dx. All right. When you do this, you actually end up with the volume as pi over 2. All right. And that's it for the washer method. I didn't include any around the y-axis, but it's the same concept. It's going to be right minus the right function squared minus the left function squared, and then you take that and integrate from bottom of the region to the top of the region. So that's it for the washer method.